thank you for inviting me to present here. Excited that the HPC meetup is here together. Next time, hopefully more people, but still excited to be here to present and talk about Rescale, both on kind of how we started the company, why we started it, and then more in general about HPC and simulation and where that's going in the future. All right, so what is Rescale? So Rescale is a company that's developing the platform for cloud high-performance computing. And it's really a cloud simulation platform, so really focused on compute-intensive workloads across a variety of different industries, and to be able to deliver that to anywhere from small businesses, but especially also focused on the enterprise where high-performance computing and simulation is used most heavily. And so I'll give you kind of a little bit of a snapshot of where we are today. So we're based in San Francisco. We're a company that has a global presence, but it's growing very fast, and most people are based here in the US. Our customers are global, so we have customers in North America and South America, in Europe, in Japan, many other countries. But especially where simulation is heavy, where aerospace and automotive are kind of most prevalent, that's kind of where we started, and that's where most of our customers are. So the products we provide are a web platform for engineers and an IT administration portal for the IT folks to be able to deploy easily this kind of solution into the enterprise. Also, as I go, if you have any questions, feel free to stop me and we can discuss in detail. As far as the infrastructure backing, we have over 30 data centers globally. We have the largest network of HPC clusters in the world. We have a broad variety of different software partners as well. And these are highly focused in the kind of CAE domain, but we've been expanding to other areas such as life sciences, reservoir simulation, and other applications as well. As far as security goes, this is kind of one of the key things when we started this company about 4 years ago. The most important element in being able to deploy any type of cloud solution is typically security, especially with the customer set being in the aerospace market or automotive. It's very difficult to be able to convince a customer to move something from on-premise to cloud, especially 4 years ago. And I think more lately we've seen a big change in that, and the reason is I think a lot of enterprises are starting to realize that in the cloud it's more of a security-first model versus the on-premise was, put everything inside of the firewall and make sure you have a really good firewall. But what companies realize, and Target is a good example of this, once that firewall is breached, essentially all the information is available to somebody. Versus cloud, it's typically a security-first model, which means everything's encrypted. Individual users are encrypted with different sets of keys. So even if you break in, it doesn't necessarily mean you immediately have access to all the information. As far as the customer base, like I mentioned, we started, and I'll talk a lot more about how we started, but we started in aerospace. So that's kind of the initial vertical we attacked, and then we've expanded to automotive. And so about 70% of our market is aerospace and automotive. But we've also seen adoption in energy, life sciences, and other kind of broad applications like EDA and anywhere else where essentially simulation is an important component of the development process. As far as investors goes, we've been able to, and very lucky to be backed by some of the kind of big thinkers in the Valley. And the reason they've backed Rescale, I think, varies. But a couple of good examples are Bezos, Peter Thiel, and Richard Branson. Obviously, they're all pretty excited about what's happening in the aerospace and space in general. But a lot of them are also understand kind of the deeper level. And so, for example, with Jeff, he really sees what's happening with Amazon Web Services. He also has a space company called Blue Origin, and he sees what's happening there. And he actually understands a lot of the different dynamics happening in aerospace market and in the infrastructure market. And so Rescale is really a company to try to bring both that engineering simulation, the hardware, and the computer science behind all this together. I think to really understand Rescale well, you have to really understand kind of how we started, and why we're so passionate about this and why we think this is a really big deal. So myself, my background is originally trained as a mechanical engineer and applied mathematician. So my first job out of school was working on a developmental program which turned into the Boeing 787 program. And the first job I really had was to try to optimize the structure in the tail. And so in aerospace, reducing weight is a critically important component of the development process. And to give you an idea of the importance of this, if you have a single pound that's on the aircraft, when Boeing delivers an aircraft and has an additional pound on it beyond what they sold the airplane for, this costs them $1,000 out of pocket when they deliver the airplane. So if you have an order book of 1,000 planes, this is $1 million per pound, just cash out of pocket. Not only that, if the aircraft is in general very heavy, it's difficult for certain airlines to buy it and use it for specific city pairs. So if you're talking about an airline that's trying to buy it to fly from Seattle to Tokyo, which would be like a typical route for the 787, if you can't meet that city pair, you have a kind of this vicious cycle. So what happens is you don't have enough fuel in the aircraft to make it because it's too heavy. So you have to either add fuel, which means increasing the fuel tanks, make the takeoff weight of the plane heavier, and it causes this kind of spiral effect because now you have a higher takeoff weight, which changes the entire kind of engineering calculations behind the aerodynamics, behind the structures, even how the plane's manufactured. And the 787 was a typical program where there's a weight that's promised, and often once you get into the detailed design, the weight starts kind of skyrocketing beyond the original target. And then at the end of the program, you try to bring that down. Unfortunately, with 787, it was extremely challenging with such a intensive there was a new supply chain model as well, so it was very difficult to be able to react to kind of all these. We had a technological change, which is going from metals to composites on the actual aircraft. We had a new supply chain model at Boeing, and on top of that, it was a very difficult and challenging program for a management where we're trying to manage all this, a different program manager every 9 months. So a very difficult environment to be able to really have a very specific, deliberate product development process where a lot of the engineering work is done by partners and where you stay in control of this process. And so because that process was a little bit out of control, essentially what happened is the weight really crept up to a point that it was critical to reduce the weight. And so a couple of years into that, I switched roles and went over to the wing development group. And so the wing obviously is one of the most critical components of the aircraft, and that's where we kind of really developed the optimization methods for the first time in industry to be able to, at scale, do a true multidisciplinary optimization. And what multidisciplinary optimization is, I was at the same time completing my master's in aerospace at University of Washington, and we wrote a paper on this that's available. It's called Composite Aircraft Optimization. And what we did is, for the first time, took the true kind of commercial tools being used for aerodynamics, combined those with structural analysis, so FEA type analysis, and manufacturing constraints for composite structure. So combining all these together, very difficult problem and very hard to compute. So a single problem might be, for a CFD, for the aerodynamics component, might take a few weeks to solve on a large cluster. When you combine these components together, you essentially get an exponentially larger compute problem. And on top of that, you try to layer over that optimization algorithms and mathematical tools to explore the design space. Every function evaluation is essentially this large HPC computing problem. And that's the problem that we set out to kind of solve for the 787 wing. And so, we had a lot of challenges there. So first of all, this is kind of before cloud computing. So we're running on on-premise HPC clusters. And we tried a bunch of commercial packages, but there was no real tool to allow you to scale this size problem on multiple HPC clusters. And so this is the first time that we solved a problem like this. And we had a lot of bottleneck scaling challenges. 2.5 years later, kind of fast forward, we were able to get something together that would work only for a 787 composite wing, but we were able to solve the problem. And we went from a process that would take 3 months internally to design essentially a new design cycle for the wing to 24 hours. So it's about a 90 times improvement on cycle time. And in 24 hours, we were able to turn around a brand new composite wing design. So that was really pretty revolutionary in the simulation world of being able to turn around a model and fully automate all those different processes. The other part, which was also very interesting, is that the wing design that we came up with, so because it took us 2.5 years, we actually were the program was delayed a bit, but there was already a finished wing. So we had a baseline to compare against that was essentially the the best possible wing that Mitsubishi Heavy Industries and Boeing together were able to design. And so this new wing that we algorithmically computed with this multidisciplinary optimization model was about 150 pounds lighter. And so 150 pounds, that's $150 million cash out of pocket. Total cost savings from that entire project was about $180 million for Boeing. And these are direct cost savings. These aren't hypothetical engineering time savings. This is pure in weight savings and actual manufacturing optimizations. And so what that taught us was it's very difficult to build this kind of system, but if you build it, it's extremely valuable. And so with that lesson learned is essentially how we kind of realized, look, it might be very valuable to have some kind of platform to let people do this easily. Because not every engineering group, and we had PhDs in math involved in this, we had hardware experts, we had computer scientists, obviously, aerodynamics experts, mechanical engineering experts, from all these different groups involved in getting this to work. But really, it should just be a few engineers who come up with this design and press a button and get the perfect design. That's the ideal state. So we had this idea, it'd be great to do that. But unfortunately at the time, there's very few companies that really had the horsepower to be able to solve this type of problem. And it was very difficult to write the software in a robust way to be able to scale this out for like an enterprise organization. But to dive a little deeper, for any kind of product development process, what we saw as very valuable is if you can automate these different components, all the simulation components of a product development process, you start having the ability to basically run the product development time, reduce that, run that much faster. What that allows you is to move back up in the conceptual design phase and make much better decisions. So much beyond this specific example of, with the 787 wing, we were very constrained because most of the decisions had already been made. What material you're going to use, which engines were going to be on the plane, how many seats. So all these things were already fixed and locked in. In fact, even the outside shape, the piece of titanium that actually builds, that you layer on kind of all the composite materials, that piece was already made. And it takes 3 years to make that piece of tooling. So with those kind of constraints, we didn't have that much freedom. But if you have these tools and you had a platform like that, what that would mean is that you can actually move up in the conceptual design phase where you can make much better decisions on across the entire product development process, making a choice like, let's make a composite airplane or a metal airplane. What are all the effects of that? And this is not just in aerospace, this would be the same thing in automotive, same thing in energy, in reservoir simulation, and any type of physical product where you're using computer-aided engineering tools. Now, that was kind of how we started. Then my co-founder, who was my boss at Boeing at the time, he left. He went into cloud computing, kind of consulting work. I left and I did my MBA. And then we joined back up a couple of years later to actually start the company because a couple of major trends were happening and this is about 4 years ago. So when we started the company, and this statistic has stayed pretty much the same, HPC in general is a huge market. So it's about a $31.5 billion market if you count the hardware that gets sold and all the middleware and all the other components that are sold as part of HPC clusters, right? But only less than 3% is actually in the cloud. And there's a couple of reasons for that, right? There's security, there's performance, and a bunch of other things. But in general, this is a huge opportunity, right? Because if you look at it on the surface, and I think people in general overcomplicate these matters. If you really look at it in general, it doesn't make any sense. It was the same thing with web servers that was happening 10 years ago, right? So everybody was buying their own servers. Everybody was buying their own Oracle system on top of that. Everybody was deploying these very expensive IT labor to kind of make this all happen. And that entire dynamic is still happening in HPC. So if you look at what happened with web services, that's all now transitioned, right? And everybody believes now, sure, if you start a startup, it's great, you should be running on AWS. With HPC, if you talk to most of the experts, they say HPC, this is a very specialized industry. It's a niche industry. It doesn't make sense to go to cloud because of performance, because of security, because of data transfer. And so what I will propose is that all those are addressable problems. And with Rescale, we're addressing all of these. But they're all very solvable, and they're solvable. Most of them have already been solved. And they're all fully solvable in the near term. And what I will propose that happens is that over the next 5 to 10 years, you'll see a huge shift, and this will be 80% cloud in no time. Within 7 years, this will be 80% cloud. And so the reason that you might have heard a lot of things about why cloud is bad for HPC, there's a good reason for that, right? So the people who own most of the market share in cloud, this is a business that, or in HPC, it's a business that hasn't really changed in the last 20 years. So if you look at SGI, Cray, all these companies, most people think they've died. They're actually still around, and they're still selling all these systems. And they're kind of a little bit conflicted, right? If you look at a company like IBM, they've acquired SoftLayer, but at the same time, they still have a huge division that's selling on-premise HPC clusters, because that's the business they have. That's all the processes they have in place. That's what they know how to sell. And so that's really the old school. And so the new school, you have Rackspace, Amazon Web Services, Azure, SoftLayer, all these companies who've developed and have seen this market for web services, and to be able to sell a single server and be able to pay for that on an hourly basis. And what you're starting to see, and that's the 3%, is that people are starting to realize this is a technology curve that's quickly, their initial launch of Amazon Web Services, if you talked about like a latency between two servers, you're probably talking about something that's 100 times slower than a typical on-premise HPC cluster. So 5 years ago, when you went and took your CFD workload, plopped it onto AWS, and ran it, you'd get miserable results, right? But that same interconnect speed, without changing any of the hardware, has been improved to by about tenfold over the last 2 or 3 years, right? And in the next 2 or 3 years, also with some hardware improvements, this is going to come very, very close to the performance you'll get on an on-premise HPC cluster. And for 95% of the applications, the performance is already there. And the only challenge is what you see in the market is all these existing players. And what people know how to do is how to buy an HPC system and from HP and plug it in to their, next to their existing system they have. And so where you see the first movers in this market is really on overflow. And so, and I'll talk a little bit more about that, but an obvious benefit is if, the biggest challenge on these HPC systems, they're very expensive and they take very long time to procure, versus a web server you can turn on instantly and they're very cheap, right? And so you see this big kind of shift happening, but this will happen much faster for a couple other reasons as well. So the other reasons this will happen is that the cost of hardware is coming down dramatically. And this is both in the high-end specialized hardware that HPC clusters use and in the low-end commodity hardware. And you see it more in the commodity, but it's happening in the high-end as well. And what that really means is that it's really not a hardware game anymore. It's really much more about the economics and how efficiently you can run your data center. And so the real costs are really around power and energy and cooling, right? And this is a very difficult problem, and a lot of the HPC experts know about this, because once you plug in that system, how you optimize your power and your cooling has really the most effect on how efficient your HPC cluster is running and the real overall cost of your HPC cluster. So today, if you buy a cluster, it's already, the total, if you look at the total cost of ownership, less than 30% is the actual hardware cost of the servers. So it's already a smaller, much smaller component than it was, 5 or 10 years ago. But in 5 years, that cost is going to be so minimal, it really doesn't matter anymore. And so then running your own on-premise cluster is much more expensive than running in a data center where you have these huge economies of scale, like something that Amazon provides or any of these other providers. So the other part of the market, outside of the hardware, you have the simulation software market. And this is a sizable market, not as big as HPC clusters, but like CAE software and simulation software in general is a very critical component of some of the most technologically complex products in the world. So anything in space, obviously all the stuff that Tesla is innovating on, all of these rely very heavily on all the simulation tools that are involved in the product development process. And it's also the core piece of where a lot of the competitive advantage for a lot of these companies come from. So expertise in that field and how well you know how to run the simulation software, how you can match it to physical test is critical in developing next generation products. And in general, if you look at the overall trends, this is, the reason it's such a fast-growing market is because it's becoming increasingly important. So companies are realizing if you have great simulation tools, right, it really comes down to having a few expert engineers, just like in computer science. You just need a few really great coders, right, to write very complicated, very complex software. And if you have a few experts, those can scale. You can scale those 10, 100x, right? It's the same thing for engineering. If you have really great experts in how fluid dynamics works, you really need a few of those experts to build your models. And then it's really just a matter of iterating through all the designs. And so relying on simulation software becomes even more critical when it's less of a get as many engineers as possible and just make the product. It's really much more about have the best possible engineers and have the best software. Because if you have the best software, you can really understand the physics behind everything and develop next generation products. The other part of the complexity of simulation, which is increasing, is increasingly it's becoming important to connect different simulation tools together. And a simple practical example would be to use a company like Tesla again. So for Tesla, when they design their battery pack, it's much more than just a battery, right? So you have the battery pack, which is on the bottom of the car, actually serves as the key structural member to hold everything together. And not only that, this battery pack influences all the noise, vibration, hardness testing that most automotive companies rely on to be able to build a product that can last a long time. It's also a crucial part of the crash testing, right? So when you do the crash analysis on the Tesla car and you have a battery pack in there, the way you design that battery pack directly affects how that crash test happens and the performance of that. And then you have the battery engineers who want to just design the most optimal and efficient battery. So you have all these different disciplines that are all coming together. And it's very difficult for a single engineer to really understand all those. I would say almost impossible. Maybe Elon can understand it, but pretty much nobody else, right? And so if you have all these experts, if you could connect these simulation tools together, you can actually leverage the expertise from these highly complex disciplines and through essentially mathematical algorithms, look at, as you change the design, how does it affect crash? How does it affect the battery density, the ability to retain energy? How does it affect the smoothness of the ride, the vibration within the car, and all those components? You could do that all together in one model. And we're not completely there yet, so it's not possible one push button, design a car. But that's where all the newest innovations are coming from. They're all from multidisciplinary type of analyses. The other part that's happening is product development cycles are rapidly decreasing. So the time that it took Tesla from concept to actually produce the car is about 3 or 4 times faster than the time it took GM to do the exact same thing 3 years before that. So with that rapidly decreasing cycle, it's even more important to be able to do that entire product development process a lot faster. And so if you rely a lot on simulation tools, it becomes critically important to run all those simulations as fast as possible, get all those insights, and come up with the best possible design.
So, one question here.
Yeah.
Assume Tesla, for sure, identified that the battery is critical to their car.
Yeah.
They need a better battery. How do they handle it? They create a separate subsidiary investing today, so they give money with a focus on development of this battery, or how? The same company? Or?
So hold on one sec. I need to get battery for that. The way Tesla themselves, now I'm not an expert on the exact procurement process there, but the way Tesla does, it's usually co-development, right? So at Boeing, I know it a lot better, but basically at Tesla, my understanding is they procure a relatively standard battery, but the way that you shape that battery is kind of up to you as a designer. You can buy batteries in all kinds of different sizes and shapes, and so the actual reliability of that battery and all the testing that goes along with that, certainly the crash testing and all the other components are all done by Tesla. But the actual chemistry in the battery and the production of that is done by a third-party partner.
So specific, what about this new factory they built in Reno, in Nevada? Is that the battery that you're talking about? Or
So that's a new. I mean, that is a joint venture. So Panasonic is closely involved in building that. But essentially, the bet there, and this is what I understand from it, is really that to really get to the scale that you need to make an electric car affordable for every person, what you essentially need to do is produce them at a scale that nobody is producing them to today. So, and this is kind of a typical move from Elon. I'm sure he asked Panasonic, why don't you set up a bunch of factories? Because I want to, in 5 years, I want to buy this amount of batteries, and nobody can produce that today, right? And so, but Panasonic doesn't want to make that investment, right? And so what they basically do is negotiate some kind of deal where Tesla makes a huge investment, Panasonic makes a large investment as well, and they start building all these factories under the assumption that they'll be able to sell all those batteries in 3 or 4 years. So it's really a co-development process, but I would say that somebody like Elon actually really understands all the details in how all this stuff works, right? So he's done all the math on at what scale does it make sense. Like, in 3 or 4 years, what does the price point of an electric car need to be to basically get to mass market? And that's the huge opportunity that Tesla's after, right?
So they use Rescale for some reason in this process?
Well, I can't talk about Tesla specifically, but in general, any type of automotive manufacturer, we have a large set of customers in automotive, and they use Rescale for various elements. So both for things like battery analysis, for crash testing, for aerodynamic analysis, for vibration analysis, for internal combustion engine development. Those are all customers who are running on Rescale today to do those simulation components. Yeah?
So what you mentioned earlier about this, the whole system simulation, I'm sure every team wants to be able to do that if they could.
Yeah.
So what is the biggest obstacle today? So with Rescale, clearly the computation power is no longer the constraint.
Yeah.
For other tools, can CATIA talk to a CFD simulation and the whole design package? Now you're talking about more different companies trying to get the tools to work with other companies' tools.
Yeah.
And then are people, what's the other thing I'm trying to say is this, so even though the tool might be ready, but people don't necessarily have the skills or the experience actually integrating them just yet. So is that, would you consider that to be an obstacle for the growth of your company?
Sure. I think it's a very good question. So this is a key challenge for any company, is to actually integrate these disciplines together. It's not straightforward. You can't just plug these modules together. What we do at Rescale as a couple different, I'll get into some of the more details around that later in the presentation, but it's really provide the platform to, what we do is tune and optimize, if you will, the software packages that are being used, right? So for example, for crash testing, one of the industry kind of leading packages in that space is LS-DYNA by Livermore. So that software package, what we do is make that run as optimally as possible on the hardware, right? And then for structural analysis, you might use something like Nastran. And for that package, we optimally tune the hardware and all the different middleware layers to run Nastran. And then once you start connecting those together, you can either use third-party tools. So there's an entire kind of set of, they're not simulation tools, there's CAE in the CAE market, integration tools that'll help you kind of connect these pieces together. But that's still a very challenging component. It requires a lot of expertise on how do these models talk to each other. And also mathematically, if you really try to solve these problems, you need a really good optimizer that pulls in essentially all these derivatives. So as you change the model, what's happening to each of these designs and all those function evaluations, and how can you combine that together in one single optimization algorithm looking at all these function evaluations at the same time. And there's commercial tools to help you do that. And I would say the leading companies in this space, what they do is they have kind of their own algorithms. And so what we do at Rescale is help them run. We kind of bring all these modules available to the user, and then you can connect them together using some workflow components from Rescale. You have the option to use a commercial tool. You also have the option to use your own in-house scripts and algorithms. And so most companies are already doing this today. They've developed their own algorithms, right? And so we just kind of supercharge the ability to run that algorithm. And so what we do in that case is essentially this exact same optimization algorithm they're running in-house can now be powered with as much software and hardware as you want on Rescale, right? But the expertise to be able to connect those is it is a very complex discipline in general. And it is something that, we do have engineers at Rescale that help with that. There's some best practices. Some of these software companies, they build tools together, but that's still relatively early. So that's exactly why, as a company that doesn't invest in this, you wouldn't be able to just, connect 5 different commercial tools together. But certain tools, they work really nicely together because they've already had a lot of customers that kind of wanted that, and they've developed that themselves.
So, this is an opportunity. You just said now that if I'm an entrepreneur and I have an idea how to incorporate all the tools together into a solution,
yeah,
I can create a company and run it on Rescale.
Yeah, absolutely.
Right.
And so
what stops me from running it on AVS and all the others is that because you are what?
Sure. I think it's a question we get often. Why don't we just go to Amazon Web Services, right? And so the answer is pretty simple. Is well, first of all, most of our customers, in fact, our best customers, they've tried Amazon Web Services and realized, hey, here's a couple of challenges that aren't solved out of the box. Because Amazon Web Services is really the kind of core platform to be able to provide a server to you. And what they work on is all the developer tools to make that really easy for somebody in IT trying to code these things together, or a startup that's trying to build their stack. And they have really great security, but that security only exists if you follow all their best practices and actually build a solution for your enterprise that is highly secure. And what we've done at Rescale is really solved all those challenges around security, around the platform to be able to actually easily run a piece of commercial software, all the tuning about how that software runs on that hardware, and all the glue to help make this happen, right? And so what I'll show you in the demo is kind of how the platform works, but really the experience that an enterprise is typically looking for is how do I quickly and easily roll out a platform that enables all these engineers to use HPC and run the simulation tools that they want to run, and do that in an elastic way. And so what Amazon provides is all that hardware in a great way for computer scientists to use it. But it's really not built in a way that a company, and many companies try this, but it's really not, Boeing's job to go build the entire IT stack on top of Amazon Web Services to be able to enable HPC in general and then enable all the specific tools that they want to run. What they really want is just an elastic, easy tool that they can plug into and have all their existing software already work on and have engineers start using it right away. And so that would be the key reasons. And the other reason is HPC hardware has all these different requirements. Depending on your workload, Amazon might not actually provide the exact hardware you're looking for. So there's all these different infrastructure providers. And so to be able to actually lock yourself into only Amazon, it does lock yourself into whatever Amazon decides to build in the next 2 or 3 years. So if somebody else comes out with a low latency InfiniBand type solution, and you want to switch to that, now all of a sudden you got to build your whole stack all over again on this other infrastructure. And so what we provide is a nice seamless layer for you to get access to whatever you want. And we'll say Amazon's a leader in this space, right? And so if you're looking for a great piece of hardware, there's a good chance it's going to come from Amazon. But if you're looking in HPC, sometimes for very unique hardware, really high RAM, specific GPU, some really low latency interconnect, you might be looking elsewhere for that hardware. Yeah.
So I see that about the vendor software licensing, sort of the legacy software licensing. How does that fit into when they try to move their commercial simulation packages into this cloud environment?
Yeah.
How are they constrained by the costs of a sort of a legacy pricing scheme? Yeah,
very, very good question. I'll get to that. Let me know. Ask the question again if I don't answer everything. Yeah. So just quickly, I think we talked a lot about this. Simulation is a critical component for all these industries, and that's what makes it so valuable. That's what makes a company like Rescale, a multi-billion-dollar company. It's because what it does is for all these industries, it provides the platform to be able to innovate and develop these products in a way that was never possible before.
So you said multi-billion, what? Valuation, sales?
It's a multi-billion-dollar opportunity. And as Rescale, we're going to be taking that opportunity. So, but it's not just limited to these sectors. So there are, there's areas where, because of the dynamics of the industry, like financial modeling, it's a little more challenging as a company to deliver a service, certainly as a startup, to like a high-frequency trading house from Goldman, right? So you have a whole other set of challenges there. But in the future, all those financial services companies are also going to be moving towards the exact same, because they're solving the exact same architectural problem as engineering simulation software vendors are. So, I've talked a lot about, obviously, the benefits. The key challenges are really around security, the hardware performance, and software availability, as you asked. And what I would also say is it's really about the full platform is really what's important. Because if you have any of these smaller components, it's not enough to really address the full solution for a customer. And Rescale addresses this. And so the key thing that we solve for a typical organization is really as you hit these peaks, right? So when you go through a software development process, what happens is you end up hitting peaks in the simulation requirement and in the hardware requirement. And depending on the process, it's just a notional diagram, but essentially what happens is that as you hit critical design, you need to finish and do all your crash testing, and you need to make sure that all your crash models line up with your physical tests that you're doing at a certain point in your design cycle. And it's the same for automotive, for aerospace. The bottom dimension is just slightly different. Obviously, an aerospace program takes a little longer than a typical automotive program, but the concept is exactly the same. And so if you look at this, as an enterprise IT guy, you might be looking, okay, where do I build my cluster, right? And that's always been kind of the question before. And so an engineer would tell you, why don't you build your cluster at the peak? Because engineering time is critically important. I don't ever want to wait, so build it for the peak. Problem with that is A, it's very expensive, and B is you have all this hardware sitting around doing nothing. So as a CIO, you might be thinking, this is great, I'm servicing my organization, But if I look at my own economics and my own performance, I'm not doing so hot because I'm spending all this money to achieve a goal that would be achievable at a much lower cost. Then you can build your cluster somewhere in the middle, and that's what most companies do. So what that means is, at critical times, people are getting kicked off the cluster, engineers are getting frustrated because essentially the product development process starts getting elongated. This is why a lot of programs end up taking much longer than companies expect, and it's not just simulation, but simulation is a critical component because you get a physical test that comes back, you got to redo a bunch of simulation. If you could do that all immediately, you'd be able to respond to that right away. If you have to wait in a queue and your jobs don't run until a few days later, there's all this context switching, there's all these other effects that happen, and it really delays the product development process significantly. And what you can also do is invest even lower, and then the IT guy proudly says, we have 99% utilization of all our hardware, right? That's great, but that really means your engineers are waiting all the time. And yes, you can prioritize jobs and you can kind of queue things and try to give the right people priority in the cluster, but that's really not a satisfactory solution because the other costs in the equation, which are the simulation software and the engineering time, are way more costly than the hardware. And so the challenges for an IT organization is how do you optimize that and still, for the IT side, and service the engineers and service management in what they really need to be able to run the product development process as quickly as possible.
So, quick question.
Yeah.
So this is, of course, this is a scalable computational resource. How about CAE license seat? So this
Yeah, very good question.
I only afford to buy 5, but in crunch time, I would love to have 20.
Yeah.
So maybe you guys say, hey, you can come to me for 20. I rent you 20 for 2 days.
Yeah. Well, I'll skip. It's the second time he asked the exact same question, so we'll just skip over to that. So really, what we've done at Rescale is we've partnered with all the leading vendors. And so not only can you go run all your existing licenses directly on Rescale, you can purchase additional hourly licensing with select vendors on this list, but ones that are included are like Siemens. All of Siemens' PLM software is available hourly for purchase directly on Rescale. LS Dyna, CD DAPCO, AVL, Convergent Science, these are all packages you can purchase hourly directly on the platform. And this is also all the ESI packages. This is really a paradigm shift, right? All these companies, within a few years, they're going to be providing hourly licensing. It's really just going to be a question of at what price point and what multiple of a prorated annual seat. Because they've all been selling annual seats for the last 15 years. So it's not that easy for a public company to say, hey, we're just going to switch over to an hourly model. It has all these implications across the business, both for revenue recognition, for the CFO, for the sales team. It's, how do you do your commissioning structure? It's completely different. For even the engineering team and development, the way you might go to market with some of your products is very different, right? And so this has implications all across the organization. But there's many, there are examples in the kind of Fortune 500 space where people have made this shift successfully. And CAD, has some examples, right? Like Autodesk has made this shift successfully. And there's like a little bit of a drop in earnings, but after that, they've been doing great. And so what you see is, in CAE, it'll be the exact same shift. But you have to be very deliberate about it if you're a large company. If you're like a Dassault Systems, you really have to be careful about where you set that price point, make sure you don't cannibalize revenue and things like that. But the reason all these partners love to partner with Rescale is because what we help them do is help engineers get access to the licenses they need and help them deliver their software much more easily and let them run it on as much hardware as they want. So if a customer has a hardware challenge of, hey, I'd love to run a bigger problem, I just don't have the hardware, they can send them to Rescale and they can run a much bigger problem, right? And for a consulting company, for example, they might be thinking, this would be great. Unfortunately, I have to buy this annual license, right? I'd love to run this set of simulation problems, but unfortunately, this project only lasts 3 months. So I'm not going to buy 50 seats of this software that I need to run this analysis in this short amount of time because I can't afford it, right? And so that's why a lot of these vendors started providing kind of monthly seats already. But hourly is really the future, and even by the minute, some of these are doing that already.
So all of these are already providing on-demand?
Not all of these are, so all of these are partners. Not all of them are providing on demand, but all the ones I mentioned that are providing hourly, those are all available today. You can purchase them direct through Rescale.
MathWorks. I'm asking specifically MathWorks or Schrodinger or.
Yeah, so the other ones, MathWorks, Schrodinger does have some pricing model, but you know, MathWorks, you can always bring your own license. And in MathWorks specifically, you can actually compile your algorithms as an executable and just run that on Rescale without any licenses being required, unless you're using specialty kind of toolboxes. But you know, the biggest and the important point here to remember is, you know, in specific cases, yes, licensing is going to be a challenge, and the price points are also going to be higher than a prorated annual license. So you don't get it for free, right? Because these software vendors, you know, they're not just going to give you the exact same thing for lower cost. They know their licenses aren't always being utilized 100% of the time.
Well, we dealt with this problem a lot when we did this resource management software, like Grid Engine, for example.
Yeah.
So it is not one single answer to the question. What do you want the licenses for? You want them to give you 100% utilization? Or you want them, for example, that no engineer should wait more than 10 minutes for a result, or half an hour, whatever it is. And that creates a different type of problem. In one, you have to buy an oversupply of licenses to create this abundance that they don't have to wait.
Yeah.
And the other one, because this thing about 100% utilization, with the cost of the software, is not such a big deal. You know, I mean, the cost of the hardware is not such a big deal. I
Yeah.
mean, okay, so I'm not using it 100%, so what? You know, I mean, as long as you pay for it in a cloud, you pay for it anyway, right? How do
Right.
you charge your cloud? Whether you use it or not, you pay for it, right?
Well, on Rescale, no. So on Rescale, you only pay for exactly what you use. If you're not using it, you're not paying for it.
Difference with AVS and all the other guys.
Yeah.
Which I have to buy about 5 different programs to find out what I'm using in order to optimize the number of CPU that I'm buying, right?
Yeah. So I think that is really going to shift, and the reason is what I mentioned earlier. You know, hardware cost is going to go down to zero, so it's really going to become about energy, and a cycle of a compute cycle is basically going to get really, really, really cheap. You can essentially think about it in 20 years out, it's essentially free, right? Certainly the cycles we're running today are going to be free in like 10 years, right? But you're going to start running more, and so that's going to get more expensive again. But essentially, if you think of that as free, the way that you solve all these problems is very different. And the way even that a software vendor thinks about selling their software can be very different, because the types of problems you can solve is when you have access to 10,000 licenses for a couple weeks. The way you solve problems is completely different than if you're constrained to 2 licenses for a year. And so, and it can be very beneficial to the right, like if the software vendor actually provides it and thinks about that in the right way, basically by going to hourly and going to relatively low price points, what that means is all of a sudden people stop thinking about, what am I paying for this software license, and start thinking about how can I solve this problem. Think about having unlimited software and unlimited hardware available to you. How do you solve the problem, right? And in the case of open source on cloud, you're already getting pretty close to that, because cloud hardware is already really cheap. And you're already talking about, if for some of the pricing plans on Rescale are like 3 cents a core hour, right? So if you're talking about 3 cents a core hour, you really got to be running a huge amount of cores for that to get really expensive. And don't get me wrong, it's very easy to run a lot of cores, and it makes sense to run a lot of cores. But if you're running open source software, you're already in this kind of paradigm, and the way you solve problems in that paradigm is very different than the way you solve problems if you have only 100 cores available to you within your enterprise and only 5 licenses and seats of Fluent. The way that you think about building and solving those problems is very different. So a couple other things, here's all the locations, right? So people, and certainly people outside of the US, very concerned what's happening to their data. Where is this being stored, right? And where do they want it? There's obviously legal challenges, Patriot Act, NSA, and all these things going on that are making people kind of a little bit afraid of the cloud. In Europe, The way you solve that problem is we just deploy everything in Europe. In Japan, if for an automotive manufacturer in Japan, if they want it in Japan, they can. In Japan, the power costs are about 3 to 4 times more expensive than it is in the US. So it really just comes down to business decision. How important is it for you to run your simulations in your country as opposed to in another country where it's actually a lot more economically efficient just due to the power costs? And every company makes their own decisions in that. But it's really not anymore a question on, if I can do it. It's really just, what's your business model and how important is that decision for you? I won't spend too much more time on this kind of point, but basically, if you look at across the organization, it doesn't just benefit, engineers and IT, but it really benefits every single group within the company, and certainly executives and management. If you want to be the company that's developing the next generation aerospace products, the next generation automotive products, or even in new fields that are just getting started, simulation is just absolutely critical for these. So security, I don't know if people have questions, but essentially the security problem has been completely solved. There's industry standards like SOC 2 compliance, and Rescale, we go through this audit every year, and this is expensive and complicated, but essentially for all of our enterprise customers, they get a full report of every single policy, control, and procedure that we follow to keep their data secure in the cloud and make sure it's segmented and separate from other customers.
So you produce the security software, or you use a third party that in your infrastructure in order to create?
Yeah, good question. So this is the reason that for Rescale it took us about 1.5 years to really get started, is because our first customers were in space. So we needed really high security levels. So we built all that ourselves, because for a cloud security model, even today, a lot of these paradigms are changing relatively quickly, right? And so for us to be able to stay with the latest security models, we've built our own security solution on top of all our infrastructure providers. And we do the SOC 2 compliance, which is an independent audit that they come in and look at how we're deploying these security solutions across all of our infrastructure providers. And all the data centers we run on also need to meet all those requirements as well. So these are highly secure data centers used by Fortune 500 companies. And then ourselves, we go through this audit. And then often with a big company, we go through one of their audits as well. So you can believe that when you're running on Rescale, anybody running on Rescale essentially gets all the protections that have been built for the highest level of kind of ITAR defense type security requirements. But you get all of that if you're running on Rescale.
What is kernel encryption?
Kernel encryption is essentially, it's a way for the Linux kernel to encrypt all the messages that are being passed through the kernel. So you can look it up on Wikipedia, but it's basically, I'm not an expert on it, but essentially the kernel has an encryption algorithm for everything passing through it.
So could you still leave the information that the users upload to the platform?
Yeah, really what kernel encryption, and this is just one small component, so a lot of the encryption happens on the data, but what kernel encryption is good for is like if by chance, now all these data centers are protected by armed guards, it's impossible to get in, most people don't even know where they are. Once you get in, if somebody comes in and just rips out like a hard drive, essentially you can't read that hard drive. So the kernel and any messages that are kind of being passed throughout the system are still encrypted in transit essentially.
But the data center owner would still be able to.
If that's so the kernel, like in all these cases, if you're able to decrypt everything. If you're seeing everything that's happening, you can always decrypt. The security is really, it's not a problem that has a discrete answer. It's really about how many levels can you build to make it comfortable for you to run your workloads in there. So there's kernel encryption, there's the actual data encryption, there's running on, in the case of like ITAR, it's running in a data center that only has US persons operating it. So these are all these different levels, right? And even as a customer, you can say, I'm going to encrypt my own data before I even pass it up to Rescale, right? So you can add as many levels as you want. Essentially, Rescale has never been breached for any reason, we haven't had any issues with security. It's really about, through these audits, pass all the right procedures to be able to deliver the best possible solution for a customer.
Do they use mandatory access control like SE Linux in the security model, or?
That's a detailed technical question. I don't know if Mark is here from Rescale.
Yeah,
he might be able to answer that.
At least some of our servers are running SE Linux.
Yeah. So, one thing we pride ourselves on is really to have all the expertise in how to deploy, really secure cloud models. And what I think one important thing to understand is that the cloud providers are generally providing the best possible security, and the reason is, and it's up here on this slide, is they depend on security, right? So if there's a big security breach at Amazon, that's a complete, that's taking what's probably going to be $1 trillion business down to zero really quickly, right? And so they are so paranoid about that, they're going to do the best possible job versus, and I'm not going to name a specific company, but any of these large companies who are just deploying and selling you a cluster, they're just giving you the hardware. And what they'll tell you if you have a security breach, oh, you didn't deploy the right firewall, right? And it's very hard to build your own, or you have to kind of go through all these steps yourself to build the same security model on an on-premise system. And the great thing about cloud is that you can scale all these things. So we just do it once for all our customers. So we can invest a lot of money and a lot of resources to recruit the best possible people to build the most secure system. And there's network effects of that, right? And so every time we go through an audit, we get another question, we do another new integration with a hardware provider, we always see kind of the latest things happening in security, and we deploy everything that's reasonable and makes sense for our customers.
So there are systems now that let you get in, but they don't let you get out. In other words, you can pass through all this, especially because you have to integrate clouds from all over the place. The idea of a firewall, it's really an obstacle to integrate two clouds when I have firewalls, among them and different security things.
Yeah.
So there is a white paper that I read from Ericsson, which is right on the website there, how they want to do it. They do it on a principle that because they have lots of service providers, each one with his own security, so they want to let people in, but make sure that if I come in, they don't do any damage. Yeah. One day I saw a guy who had a German Shepherd. He says, "This is German Shepherd, how it works? But he lets you get into the house, but then doesn't let you get out of the house." That's how it's trained to work. Yeah, maybe an interesting model. I mean, at Rescale, we believe in never letting anybody in, right? So, and the other part is that we also give, the customers still have the option. And the great thing about simulation is, it isn't, most of our customers, they store all their data on Rescale, but it's not required. So you can sync all that data, put it on premise somewhere if you really believe that that's a more secure system. But I think most of the enterprises and there's many Fortune 500 companies that are already doing this. They're realizing quickly, the on-premise might not be so secure versus like a cloud system where everything is kind of individually encrypted. So to me, what is remarkable that you have done, you have created in a couple of years, such a reputation for security that you described to us. This is only positive for Rescale, right? How it works and how it works, okay, you can make separate presentation on that, but the reputation that you are around is that your cloud is very, very secure, right? Yeah, I mean, it's critically important, right? And it's the same thing for any business. So when Salesforce started, they got all the same type of questions, right? Oh, can you really have software in the browser? Does this really work like that? I'm putting my sales data in there. Sales data for a lot of companies is some of the most sensitive data. So, it's something that in other dimensions, has already been adopted by enterprise kind of across the board, right? Salesforce is everywhere, right? So engineering data in some ways is actually more difficult to understand often, right? It's not as simple as sales data, and it's certainly more complex. And there's good reasons why some have been more hesitant to kind of move to the cloud. But I think at this point, it's really not a question anymore. And the reason is that you're seeing the easiest target
for a security breach is an on-premise system. It's not a cloud system. So, with time, I know we're kind of running a little bit over time, so I can keep going, but, I guess feel free to take off if you got to go.
Everybody wants to go.
Yeah.
I have all the time. I get it.
So really what we've built is kind of two basic solutions, right? One is kind of the best-in-class engineering simulation platform for the engineer to be able to upload their models, run this, do it kind of easily. That's really what we built, for the engineer and by the engineers often, to be able to run any of these complex workflows, to be able to easily deploy all this. And the other key component is obviously all the security and all the IT deployment. How do you as an IT manager control all that? And that's the other part of the product. So what I'll do is I'll do the platform demo at the end. So I'll just kind of go through the rest of kind of what customers are doing, right? So we talked about space a lot. So space is obviously an industry where simulation is critical, and Rescale is being used to design some of the latest private spacecraft. And this is helping develop different components of the process, anywhere from propulsion, the structural analysis, and all the different kind of controls and simulation tools that are being used to develop rockets. And then very popular application is internal combustion engine development, right? So here you have a lot of different physics going on. You have the actual combustion, you have the physical movement of a piston, you have all these thermodynamic effects. Very complicated problem, also very valuable problem. If you can get 1% more efficiency out of an internal combustion engine, this is something people are willing to pay a lot of money for, right? And so there's a lot of companies, there's obviously kind of the Teslas, which are moving completely away from this, but there's still, the main industries are still tweaking to get more performance out of internal combustion engines. And this will probably be around for the next 10 years.
Question. So likely the big companies like GM and others, they have their own on-premise infrastructure, right?
Yeah.
And it's likely to be large, and Boeing probably have the same thing.
Yeah.
So do you actually give them performance increase compared to what they run in-house?
Yeah, so that's, you mean on the, so I guess the question is it a pure performance increase or a capacity increase?
Is it both, or is it just one?
Yeah. So on a pure performance metric, if you, one thing that is true, if you have an infinite amount of money and you buy all the best possible hardware and you essentially build an on-premise bare metal system and you put the exact software that you built for that system on there and you run that system, that's going to be the best possible performance you will ever get out of that, because it's perfectly tuned and optimized. So when you run a performance benchmark, it really matters what are you comparing to. Are you comparing to a system like that? Are you comparing to the general HPC that most people have access to? That's the more typical deployment, like at a GM or something like that. Or are you comparing to the performance on a standard desktop or something like that? So what I'll say is that what we generally do is we try to provide as close as possible to that perfect system. And the way we do that is that we can tune the software and the hardware and pick it perfectly for whatever application you're doing. And every project can be different, right? So if you're doing a fluid dynamics simulation with this piece of software, you have this optimal stack, and you pick that hardware with it, and then you're doing a structural analysis, you can completely switch the entire stack. So with any large company, yes, they have different, they have a lot of capacity, they have a lot of different clusters set up, but usually they're never really tuned for one specific application because they have to be shared within the organization. Because the IT organization does have to answer for the overall utilization of this cluster. And if it's only one niche application and it's being used 5% of the time, that's not something that typically they can invest in unless it's that important and that they're willing to basically pay 20 times more for just that 5% of the time. And so on a typical scenario is that all our customers, they have on-premise HPC clusters in general. All the large enterprise customers do. But what they're doing is they're starting off saying, hey, first of all, it's great for overflow. Overflow right now, we don't have a great solution. So what we're going to do is we're going to start putting that on Rescale, right? And then they start looking at, hey, let's look at, how much does it cost us to operate one of these clusters relative to operating it on Rescale? Well, we have much more economies of scale. So it actually is a lot cheaper to when they buy a new cluster to shift that over. And then when you look at the final answer is, why are we even in the operating HPC cluster to begin with, that business to begin with, right? And then you start asking that question, then it ends up being, look, that's probably not a business that we as an automotive company really should be in. We're really good at building cars or integrating cars, right? And so that entire business shifts over to Rescale over a few years. And so we've seen that with tier 1 suppliers and large OEMs. There are entire organizations that are built around operating HPC clusters. So are they going to day one say, oh yeah, let's shift everything over? Absolutely not, right? If you run a typical performance benchmark, bake off of their best possible benchmark on their cluster versus the one on Rescale, what you'll see is roughly the same performance. Sometimes we're a little bit faster because we have a slightly newer processor. Sometimes they're a little bit better on latency interconnect because we have a couple of extra layers in the way we deploy our software versus their bare metal perfect system, right? But the reality is, if you look at the bigger picture, is if you just want hardware when you want, like when you need it, immediately and perfectly tuned to the stack, it makes way more sense to go to Rescale. So it's really about when you look at the bigger picture, it's not really the pure performance doesn't really matter. In fact, I would say in most cases, as long as you're within 20 or 30% of the expected typical performance, that question has already been answered. Yes, you can perform to roughly what we expect in-house. And it's really more a question of how much are you willing to pay to be able to get fully elastic kind of capability for overflow internally. And then long term, how much are you really paying to operate that cluster, right? And does it really make sense to keep doing that? Yeah.
So I'm assuming that your people run on bare metal. I mean, when these virtual clusters provided by the physical data centers that companies that you're partnering with.
Yeah.
They're bare metal. I was just wondering, these companies that you're partnering with, do they have a fairly rapid refresh cycle on the hardware so that your data centers are getting state of the art over time and are improving it potentially faster than what the enterprise IT environments are?
Very good question. So this is actually a big reason that companies switch to Rescale is, even if you're GM, even if you're Boeing, even if you're one of the largest kind of companies in the US, you still can never really keep up with essentially what Rescale has is a refresh rate of these more than 30 different data centers globally located. They're all refreshing at different paces. So when there's a new release of a Xeon 5 processor and you want to try it out, it's available immediately. You want this latest NVIDIA Kepler K80 processor, you can get that immediately, right? And the reason is there's one data center somewhere that's been willing to invest in that because they have a niche application that they're willing to do that, right? And it doesn't matter really what size company you are. It doesn't always make sense to go buy that hardware, even a couple of test clusters. It doesn't make sense to invest in that. And with Rescale, you basically get the refresh rate that's across all of them. There's huge network effect. So what that really means is that a typical refresh rate on most companies are doing it on a 2 to 3 year basis, right? After 3 years, they say, okay, this doesn't really make sense anymore to keep running this cluster. Let's throw it out and let's get a new one, right? And really, really good companies are on about a 1 year refresh rate, right? So that's kind of the best practice. At Rescale, we're in a quarterly or less refresh rate, right? So it's just a different ball game. And the other part is this procurement cycle, right? So when GM buys a cluster, by the time they have that up and running for engineers, you're talking typically about it's typically about a 6-month period to get that up and running, right? So you've bought the hardware, and by the time you have it up and running, that hardware is actually already old, right? And you've lost a lot of value already on that. And if you're talking about more than a year later, it doesn't even make sense to keep running on that hardware. Because if you actually start, go back to what we talked about earlier, right? Looked at like this dimension of the cost of the hardware is really just a very small component of the operational expense, right? So if energy is your biggest cost component, it's not really about that new hardware. It's really about operating this in a really efficient way. So if you have older hardware, it doesn't even make sense to keep it plugged in, because you can take the same money that you're using to operate that cluster, right? Say it's a 100 server cluster, to take that money, right, that you're using to operate that, and buy a brand new, 50 server cluster, plug that in, and you're still on an hourly basis, you're actually cheaper, right? And that dynamic is, eventually it makes completely no sense. It already doesn't make sense to run on-premise. In fact, we just have a blog post up today that's called The End of On-Premise HPC. So it already doesn't make sense, right? But companies are in the habit of doing it, and we're kind of like starting this shift right now. But once you see like what happens with kind of the cost of the hardware, cost of the energy, and all the other components, you're starting, it makes zero sense to keep operating yourself, and certainly not at the scale of most companies operate it at. All right, so people are falling asleep. So what I'll do is quickly talk about some of the other applications. So you have oil and gas, reservoir simulation, and you also have the actual development of oil and gas tools, right? So drilling equipment, pumping equipment, things like that. That's a big market. Obviously, they're going through some cycles with the oil prices going up and down. But typically, this is very lucrative industry, and simulation helps much more efficiently, essentially extract resources and use them. So it's also something that in the future becomes more and more important in these industries, because there's only a finite amount of fossil fuels around, right? And so to be able to do that and extract those efficiently, that's going to become critically important. So more fun ones are like Formula One teams. They're really on the cutting edge of how they're looking at fluid dynamics, how they're looking at structures, the interaction between those, and that's kind of a whole game into itself, where they have special restrictions on how many flops they can run and things like that. But that's another area that's like pretty exciting and pretty high performance. The teams there really have some of the smartest people in fluid dynamics and in structures, so they're really running kind of the latest technologies. And then helicopters, the entire kind of military and defense industry. This is critical area where there's a ton of simulation tools used and a huge amount of value there to be created. Rotorcraft, they're very difficult to design. And companies like Sikorsky and others, they have a really difficult challenge in being able to make helicopters safe for the military, right? And so to be able to make those safe and really have kind of implemented every possible maneuver a helicopter can make, is extremely difficult, and that's why simulation there is absolutely critical to be able to develop anything like that. Industrials, if you talk about wind energy, these are essentially these composite blades that are very similar to like an aircraft blade or an aircraft wing, and so these are also a big part of our customer set are companies that do this type of development, anywhere from power generation to turbines and things like that. So kind of on a final note, what I would say, this is really just the beginning of what is possible, right? So once you've really automated all these components, you can really start thinking about, you've integrated everything, you know how to do the optimization, then you can start building algorithms that are essentially more intelligent than yourself, right? So you're building an algorithm to help you figure out what are the best practices to design a physical object that could be in aerospace, in the aerospace industry. It could be something in automotive. But what are the best practices on algorithms to be able to develop that best design, right? So right now, even for these most complex cases, what's happening in industry is you connect all these tools together, and then you layer over your optimization algorithm that you think is going to work the best, right? And then you see the best design that comes out, and you say, hey, I have the best possible design. But really, those optimization algorithms can also be tuned. And these design spaces are essentially infinitely large to explore, right? And so if you take that to the next level, you let the optimization algorithm tune itself. And that's kind of what artificial intelligence and really kind of what some of the really future companies are looking at, is really at how do you design some of these really, really complex, you talk about 5 or 6 different disciplines that are, each of those are extremely difficult just to understand by themselves. Things like building a quantum computer or something like that, right? And so if you have all these components and you bring them all together.
We just learned in the last month that the quantum computer
Is not, yeah. Well, there's companies in this space that are taking a fresh new approach at this. So I'll say one company that's here local is Rigetti Computing. And this is a gentleman who came out of this, the IBM team. He started his own company developing quantum computers. And he believes they'll have, I think, a quantum computer out in the next 5 or 10 years. And he's got some great investors and a lot of people that believe in this.
That's what we learned, that not before 2025.
Yeah. So these are really, but this is really the future, because if you are thinking about the next set of problems, right? It really becomes these, what today seems like almost impossible problems to solve, but that's what most companies are going to be doing in 15 years, right? And what we're doing is really building kind of the platform and all the plumbing to be able to make that happen. So I'll just end it right there. I could do a demo. I don't know if you guys want to see a demo. Yeah? Okay, we'll do a demo.
How's semiconductor industry receiving Rescale?
Sure, it's a good question. Semiconductor industry, we haven't done a lot there. Part of the reason is it's an industry where you essentially have dynamics that are difficult for a smaller company to participate in. Right? You have 2 companies, Cadence and Synopsys, that control all the major kind of tools used in the EDA kind of development process. But that said, they even themselves have released little components that work on the cloud. I think, for us, we'll be entering that industry at a point once we've, fully matured in some of these other areas, because that'll make it a lot easier for us to strike a good partnership with these simulation vendors, right? The key areas for EDA would be verification analysis, place and route analysis. These are all big problems. A lot of them are embarrassingly parallel, make a lot of sense to run on a cloud system in general. But then on top of that, all the automation, there you really have a lot of disciplines interacting with each other as well. And then even if you look at FPGA and things like that, these are all perfect for simulation and perfect for trying to kind of optimize how all these different components, different disciplines come together in a physical product.
Last I heard, just a few years ago, it takes them 24 hours just to simulate 1 second
of
simulation.
Yeah.
The other one's the license. So they need to have a license too, especially
Yeah.
when you tape out.
And so that's the key challenge in that industry is, once you've locked yourself into one of these tool sets, you also got to think about it from the software vendor's perspective. If you're, Cadence and delivering that package, how are you going to, shift your model to be able to give, a company unlimited licenses, and still, in most cases, they're trying to make more money out of that opportunity, right? And if you're one of the only 2 options, you got a pretty good thing going, right? You essentially have a quasi kind of monopoly with this other player on the space, right? And if you want more licenses, buy an annual seat. It's going to cost you $250,000. Why don't you just buy another one, right? Because these are companies that can afford to buy those. But I think what you will also see is there will be smaller players, because this, the music will stop on this at some point, right? And they'll completely displace that entire stack. And there's even startups that are trying to build pieces of this, technology purely on cloud systems, right? I think that can work. But the challenge is, there's a huge amount of investment that's gone into building these tools, and it's extremely complex and complicated. So it's just a difficult industry, I think, in general, as a startup to participate in.
Yeah. In a way, it's a legacy thing. 25 years they're still making chips, right?
Yeah.
And the industry set in the way they do it, and it works, right? because they were using, you know, all these distributed resources like LSF, like Grid Engine, and they're happy with that. They have their own server there, and that's how they do it. You want to go to a cloud, then they have to think about 1 hour licenses and stuff like that. They don't want to. They
Yeah.
want to give you seats.
Yeah, and it's the same model we've seen in CAE simulation. You know, when we started out, most people told us, you know, you're never going to be able to get hourly licenses from a company like Siemens, right? It's never going to happen. Nobody's ever going to do that. Nobody's done it before. You know, people have asked for this for the last 10 years. Nobody's ever going to do it. But once a company like Siemens PLM, it's led by this guy, Chuck Grindstaff, he really understands kind of where the future is going. And he's willing to bet on the future, right? And so, you know, he took some risk in doing that, but that risk is paying off quickly, where now all of a sudden people can access his software much more easily. And if you're running, for example, if you want to run Nastran and you want to run, you know, a design of experiments with 10,000 models at the same time, there is only one economic option for you, right? There's only one reasonable option within about, you know, 2 magnitudes, which is NX Nastran, right? And so, you know, there's other competitors in the space that provide similar services, but if you're running that type of design of experiments, that's the only place to go. And that's why hourly pricing is critically important. But that's also why you'll see this kind of big shift. So I'll just quickly run through here. You know, this is the interface. To log in, you just go to platform.rescale.com. And essentially what you see here is kind of, you know, all these jobs that are in my account. And what I'll do is this function called clone. And so what this does is it makes a copy of an existing workflow setup, right? And I'll just kind of walk through this basic setup. Now the best part is you can go do this at home or at work anytime after this. To create an account is free. We even give you a bunch of simulation credits that'll, you know, allow you to run a couple hundred hours for free. So especially if you're running an open source package like OpenFOAM or something, it's all free. You can play around with it, do whatever you want with it.
You upload your own codes?
Yeah, you can also upload your own codes. So good question. So that's a more advanced feature, but yeah, you can also upload your own codes as well. So I'll just kind of walk through here. So you start with your input files, right? And so in this case, we've uploaded this already. But this is kind of a 2D airfoil model, a simple example, you know, much simpler than a typical example in the aerospace industry that's being used. But it's very representative of the exact same steps that you would go through to run even, you know, a Boeing 787 wing analysis, right? And so to upload your files, you can just upload from your desktop. And this is, again, why you would use something like Rescale, right? So if you upload this, if you use a typical uploader, like an HTML uploader, you can do that, but it's going to be really slow, right? Like you're going to be uploading through the browser, which is challenging. If you have HTML5, you know, might be able to do it a little bit faster. But this is where, you know, the engineers at Rescale have developed a multi-threaded uploader that allows you, and we call it the enhanced uploader, allows you to take large files, thread them into small pieces, and fully saturate your bandwidth to upload kind of to the maximum capacity to whatever, you know, access you have to the internet.
Is it a separate app, a standalone app?
It's a Java applet, so you need to have Java enabled on your browser, but that's it. So once you have that enabled, you upload it, you get advantage of that. Not only do you fully upload your file as quickly as is basically possible, you encrypt everything on the fly. So everything is getting encrypted, you know, client side before it even gets uploaded onto the server. And so this is the type of security that really, you know, makes it super safe. Yes, you use the same, you know, HTTPS encryption, the same encryption used for, like, if you enter your credit card in PayPal. But not only that, the data that you're entering through there is already encrypted to begin with, right? So it's really, you know, state-of-the-art technology. So once you've uploaded it, what you can do is, you know, also upload it, you know, from your cloud storage account, right? So once you've uploaded something once, you can reuse this as many times as you'd like. So what's very common in industry is that you have these large files, you know, for a load set or something like that. It doesn't change for 3 months. You only need to upload that once, right? In fact, anybody on your team using Rescale needs to upload it once, and that data can be shared within your group, and that can be done securely.
Who's cloud storage?
So this is Rescale storage. Yeah.
Not a, like Dropbox or anything.
It is, yeah, it's not that. We are working on a box integration as well, so it's relatively straightforward to integrate it with other tools. If you have your data already sitting in the cloud somewhere, you can actually port that in as part of your simulation job. So let's just say you had your data sitting in Amazon already. You could actually copy that into your cluster when you kick off your job. So it's very easy to kind of utilize data from anywhere. The only thing is when it's on your desktop, you need to get it up there first. So once you have your files here, and we zipped that, so we compressed it kind of to make the upload even faster, and this will decompress kind of on the fly. And so in this example, what we're doing is a DOE, so design of experiments. So what we're going to run is a bunch of different iterations of the same design for varying a couple parameters. And so what we have here, and what we've done is we've done a cross product, which is just literally a grid of two different parameters and different settings for each of those. So we're varying x velocity and y velocity, going from, in this case, 20 to 30, I think it's meters per second, an increment of 1, and 3 to 8 in increments of 0.5, right? So you get this grid of different points, and what this does is automatically populate your input files with these variables through a templating system. So that makes it possible that in the Rescale interface to run any kind of embarrassingly parallel type of run, right? So you can upload a CSV that has these variables already predefined if you want to use Excel to populate that. You can run a Monte Carlo distribution. You can really do any type of distribution or embarrassingly parallel run that you'd like to set up. That will populate the templates, and then automatically Rescale understands how this workflow has been set up. And that's very helpful for when you kick off the job. You can scale that cluster in the way that makes the most sense for that job.
Do you have to pay more to scale it up, or
Yeah, it's a very good question. So templates, you fill this out. So I'll skip over here to the hardware. So you don't, not only do you not pay more, you're paying for area under the curve. So essentially, for you to run a single server for 1,000 hours, right, costs exactly the same as to run 100 servers for 10 hours, right? And so you are fully incentivized to parallelize as much as possible, which means your turnaround time is going to be 100 times faster, right? And so this is a key component, and this is why these types of runs are very popular on Rescale, because it's so easy to set up and it's completely cost efficient, right? You don't gain anything by making your runs go longer and do it back to back on the same cluster. And setting up your hardware is really as easy as, here's some basic hardware types, there's specialty types. In the back end, what's happening is kind of it's really kind of just a black box to the user. That's done on purpose because you don't need to worry about, picking the best optimal possible set of hardware that this software could run, right? You get a few choices. These are already optimally tuned for this specific software package.
But is that the memory per node for each node in the cluster?
This is all per core. So,
Per core.
yeah, so you're looking at different core types. And so here you have something called the nickel core. You can even get the processor information. So this is an Intel Xeon 2680 V2, Ivy Bridge standard kind of Ivy Bridge processor. So you'll see 3.8 gigabytes of memory per core, right? This kind of interconnect speed, that price. And so now, if you go here, number of cores, right? We'll just start with cores. So the number of cores, you can scale this up to any size you want. And as you see on the right side, this is kind of scaling out, showing your cluster, right? And the cluster, in this case, has 360 gigabytes of memory. The reason is you're running 96 cores. 96 times that per core memory amount. And this is kind of deceptively simple, right? You can scale this up or down to as many as you want. You can add zeros, right? You can run 10,000 cores if you want to do that. And we have customers that easily run it up to 50,000 cores without an issue.
Now, some of the codes, you really have to distinguish between whether the cores are part of a node with shared memory,
Yeah.
or whether you're talking about the total number of cores spread across all the nodes, and because you have to worry about the allocation of memory, that the shared cores on a node
On the, yeah.
require for the, because codes may have to tune themselves, or they may have limitations in the parameters that you have based on those. So
Yeah.
you can control all of that.
Yep, absolutely, and that's what you see here. There's also a per node information on here as well. So if you see down here, you're at 16 cores, you're up to 1 node, right? So here you're like at half a node. Now you're at 1 node, and now you're going up to 2 nodes, right? And so if you're trying to optimize, and you'll see even in the graphic here, these are all cores, and that's 2 of those, right? And so that's how you can kind of balance, kind of interconnect, or and that's a very important point you bring up is sometimes it's much more important to have all the memory on 1 node than to have it dispersed across a large cluster.
Well, there are codes that just won't run if if they don't have the right balance of memory per node.
Exactly, yeah. And so what we try to do is we help the user as much as we can. So even in the command line to execute the code, you have your DMP, SMP, all those other variables. We will help you tune those, right? And it'll come up with a suggestion that's kind of recommended. But you can even, if you're an expert at it, you know exactly what your model needs, you can tweak those parameters yourself. And so once you've selected, the cores you want to run on, this is where, in the case of design of experiments, it's really easy. Let's just say we're running on 8. We can scale up the number of task slots as well. And so task slots are really just individual clusters that are going to run this job for you for that specific part of that design of the design of experiments. And so this makes it really easy to just run. In this case, we're running 4 task slots, so 4 times the cluster of 8 cores each, and that's all you need to do. And so there's more advanced. There's GPUs and other kind of more complex configurations, but for this example, we won't really get into that. And then you select your software. So in this case, we cloned this job, so we already have OpenFOAM selected. But you can have multiple software packages, and you get this big menu of all this different software. And this is not any type of secret. This software is all available right here. So if you go to rescale.com/software, all that's also right there on our website. So you can check out what packages are available.
I see games on there?
Yeah.
So the hourly price is it dependent or independent of the simulator that you're using?
Yeah, so the workflow, and that's how this has been built, to run essentially any compute-intense process, right? But you can run any software you'd like.
So I can pay, say, CATIA, and it will still be the same price as someone who's not using CATIA.
Well, the software price, in this case, we're running an open source code, so you don't see that here. But say, for example, if you're running NX Nastran, you're actually going to get a charge for NX Nastran on an hourly basis with whatever pricing model they have, right? In the case of OpenFOAM, it's free. So yeah, it really does depend on kind of if you're using commercial software, there's obviously additional charges for that. Important point to note is that the hourly software charge, like on average on Rescale, is anywhere from, for a typical run is probably about $10 an hour. And the hardware is typically much cheaper than that if you're running small jobs, right? If you're running big jobs, you can get up to even software prices of hundreds of dollars per hour, and then hundreds of dollars per hour for the hardware costs. But typically, the ratio of the software cost to the hardware cost, the software is the more expensive cost component, which means it's typically a good idea to throw a lot of hardware at the problem, which both helps you in turnaround time, but also saves you money in the actual execution of the software. So it doesn't really make sense to run on really low-end hardware to try to shave some cents on the CPUs. Because the software costs are typically higher. And that said, you can also run you also have the option on commercial code to run your own license. So you can either run from your own license server and port that to the Rescale platform. You can run on a license server set up for you by Rescale and hosted by Rescale. And in some cases, you don't need to do anything because you're just paying by the hour, and we take care of all that stuff on the back end. Yeah. And the other question you asked, which is an important one, you can also run your own software, right? So if whatever you have is not on here, there's 2 options. If it's a common package and we don't have it, we already have 120 packages, so there's a good chance we'll have what you're trying to run. But if we don't, or you have some customized package, or in the industry you have some proprietary package, then essentially what you can do is upload it yourself and compile it on the fly. And so you can actually run anything you'd like. So we can boot up essentially a hardware layer and the operating system layer with whatever libraries you're looking for, say it's a Python script or something like that, then you can get that Python version and then run that, and that's your simulation. And the other part, is you can add as many software packages as you want. So this is a simple workflow with one piece of software. But like I was mentioning, all these modules, you can start chaining these together. And there's some examples in our blog and on our resources page, which has a whole bunch of different industry examples of multi-disciplinary integration of multiple codes together. And so you can look at how a fluid structural interaction problem is set up using commercial tools like ANSYS or something like that.
So is there, do you guys provide like an API for companies to do customization?
Yeah, good question. So we have an API, yeah. Yeah, so the API will let you do everything you want in this interface, and sometimes even more, that you can just execute programmatically, so you don't even have to go to the web browser to run anything. I would recommend that initially you get a feel for what's possible by working with the browser. But I do think at scale, the experts, typically an API might be easier to execute some of the things you might want to do versus in the browser. So then, final step, not required, but you can do some post-processing. So you can take some of these results and you can essentially run a Python script to pull out some values that you might want to plot. You can create images, you can generate animations, you can do anything you really want. And there's some built-in tools. So we can also have, I don't know if you're familiar with GNU plot utility. That'll let you, it's an open source utility, let you plot kind of any data sets you'd like. And then Rescale itself in the browser, and I'll show you a couple, has some built-in plotting and visualization tools as well. So once you've set this up, all you really need is the input files, the software, and the hardware. And then you just press submit. And so what happens now is essentially this template gets fully validated, and it gets confirmed that that setup makes sense, so that the software and the hardware can run together, that your templates can populate, and it takes a couple minutes to boot the cluster, and you're up and running, right? And it's really that easy. So this is this is live, no this is just an actual problem I'm running.
Creating a virtual cluster on the physical hardware, partitioning it out according to the specs.
Yep. Yeah, and so you get it on the fly exactly what you're looking for. And in some cases, you might actually get multiple clusters, right? So in this case, you're actually getting 4 individual clusters that are each kind of this little cluster of 8 cores each. So that's that's how it works. So I'll just skip over to kind of a completed job so you can see a little bit of the post-processing to give you a feel for that. So for the post-processing, essentially you get a table of data, right? Here's all your individual runs. You can go look at some specific output values. You can download this entire run. And then you can skip over to these plotting utilities. And these are really powerful. It's very generic. So you can do scatter plots, area plots, surface plots. But really, you can go here and plot, any of the combination of variables that you'd like. And so here we're plotting the input and the output. So if you didn't understand what we're doing before, we're really just running all these individual design points for these 2 parameters, right? And these are all going to be running depending on the size cluster you set at the same time. And then, what might be more interesting is to start plotting and looking at, some of the output variables. So now we're looking at drag and lift coefficients as a function of the parameter of x velocity in this case, right? And so really using these utilities, you can start kind of interpreting the data. And then you might be saying, hey, for this specific data point here, I'm really interested in this. I want to know more about that. So it highlights it right here in your table. And then you can dive in deeper, and it'll give you all the files that were generated from this run. If there's images, you can plot those. You can view those right in the browser. If you want to download it, you can just select all files and download those. But the really powerful thing here is that if you run really large sets of data, you could actually generate 50 terabytes of data right here on Rescale, right? Which is totally, for most companies, an impossible kind of challenge to try to solve from the IT side. But you can easily generate 50 terabytes of data. You might be saying, why do I need 50 terabytes of data? Well, if you want to run, say 5 different parameters, each of them having 10 different settings, each of them spits out a gigabyte output file, you're talking about 10 times 10 times 10 times 10 times a gigabyte, right? And so very quickly, you're already up into the terabytes if you're running really serious big models. And then to manipulate that data, right, if you had 50 terabytes, just to get that downloaded will take you weeks, right? So right here in the browser, you can go from 50,000 runs that are a gigabyte each, so 50 terabytes of data, down to a single gigabyte of that you might want to download, which is like the optimal design or the most important piece of data that you're trying to analyze.
You have hourly charges for storage?
Yeah, so if you delete your data, you don't get charged anything. If you keep your data around, it's $99 a terabyte for storage and $99 a terabyte for transfers, upload and download. But you're talking about $99 a terabyte, right? So for smaller problems, if you're just playing around, it costs you basically nothing, right? So
it's a very scientific price.
yeah. So it's really just to give people a feel for it, but and help cover our costs, right? But really, storage also long-term is going to get very, very cheap, right? So we also have these enterprise plans. So if you're talking about storing, thousands of terabytes of data, right? Then you have these longer-term storage plans that can bring the storage costs down even more, right? And this can be important for like an aerospace company. They need to keep their data around for 25, 30 years. So it's an FAA requirement to keep all your simulation data so you can reproduce any analysis in case there's like repair issue or a plane goes down and you need to reanalyze some pieces of it. You need to be able to reproduce that. And so to keep it around for 25, 30 years, this is a great way to do it. How to do it before on the last aircraft program, they just have a whole bunch of hard drives that they buy and they hope they don't fail, right? And they copy it 3 times and they hope all 3 of those don't fail, right? In the cloud, we're already replicating this automatically for you. You can replicate as many times as you'd like, but essentially you have 99.9999999% reliability, right? So you can always get that data back. And even before they were storing this in hard drives, so if you talk about like the 777 program, all of this stuff is in cabinets on paper, right? So the other part is retrievability of this data. So if you keep it on Rescale, you can have as much data on there. You can easily look at, hey, how did we create that? What version of the software did we use? And what was the workflow? What were the input files? So all that metadata and that context is all retained. And so it's a much more powerful storage system than just pure storage, right? Like you have this additional layer that helps you actually understand what you're doing. And if you have a filing cabinet essentially that has all that in there, it becomes something that's not practically usable by engineers.
How did you get the output variables?
So that script, this is the exact same model that we just ran. So that script, that Python script, is looking at the output file, and it's pulling out specific variables, in this case, like drag and lift coefficients. So right here, if we go back to the run that we were actually running, it's running now. You can see here's the clusters that are up. Here's the runs that are happening right now. And you can go right in here and well, this run is just completed, so it's going pretty fast. But when you have a text file here, you can actually tail those files, so you can actually monitor progress. You can view images, graphs, anything like that on the fly as it's running. You can even do an entire remote desktop section and hook that up to this running cluster. So if you want to look at it from the user interface, that's just a typical like Windows desktop user interface. You can hook that up to this system as well. So it really lets you do anything you'd like. Some of the nicer features that cloud enable are things like this cloning, which just copies. That's how we started this job. We just copied that setup. So literally, at the click of a button, you've reproduced this entire setup. You can tweak a couple parameters, kick off that job again. And so in 2 minutes, you just were able to rerun a whole bunch of complex analysis. So you really only need to set it up once, and then you can clone that. And then the other part you can do is share that with your engineering team, right? So if you're the expert setting up this workflow, you really know how the optimization algorithm works, how all these modules talk to each other. You can then just press the share button, and if you're an enterprise, you have to be within your organization and pass all your kind of IT controls. But essentially, you can collaborate with anybody else on that same workflow. And by sharing it instantly, there's no copying of files or anything like that needs to happen. That's the power of the cloud, right? So all that user needs to do is understand how that workflow was set up, understand the parameters that they want to change, and can kick off a job that maybe has so many complex elements to it that it really requires 8 or 9 engineers to work on. But a single engineer can make their modifications and rerun that analysis. And so that's you know, a very powerful component. The other part is you know, if you need support or help from Rescale on anything you're doing, you just press Rescale support, and you get either instant help through the chat functionality, or you get email help, right?
You can call it fanatical support.
Yeah. Rackspace has already patented that.
Okay, so the last question is, who is the typical user of this? It definitely has to be a design engineer, because otherwise, it's like Timur says, you know, we have some design engineers who are very good engineers, but they're not very good in being system administrator, and you probably want to make their life a bit easier here.
Sure, yeah. Well, this is great for that application, but I would say, you know, 95% of our business is with large enterprise companies. If you look at volume of core hours, right? And so we've built this solution to really be an enterprise product, to be able to handle all the IT challenges a large Fortune 500 company has in integrating with this kind of solution. But that exact solution is available to any small, medium business, any individual engineer that wants to go run what they want, right? Now, the reality is that the most complex problems are being solved by big companies, generally, right? And so they get the most benefit from this type of system.
This comes to another thing, you know, 80% of the business comes from 20% of the customer.
Yeah.
So you have an engineer from Boeing working on Rescale. How do you convince him to use more of the Rescale? I mean, it's up to him. He said, well, I want to solve this. And
sure, I have that's a very interesting question. So, you know, we don't, obviously we like it when people use our service a lot, but really only if they're using it because they're getting a lot of value out of it. So a typical user on Rescale in the enterprise starts like this. They have a specific, you know, very specific problem that they're trying to solve. They don't have enough hardware capacity. They have an internal cluster, but they need either specialized hardware, or they need much more hardware than they have in-house. When they come to Rescale, they get special permission. We work with IT. We do all the security audits. We get that individual up and running. Okay? Very quickly, their group finds out about it, and this individual starts running some jobs, and then starts sharing jobs within that little, you know, group, right? And those individuals start running jobs. And what you see for even a specific individual, the first type of jobs they're running are just single jobs, right? And then they realize, wait, why am I running one job at a time? I can be running 100 jobs at a time, right? So then they start, there's a little bit more of a pause, and all of a sudden they're kicking off, you know, 100 jobs at a time because they figured out how to do that, right? Then they share that with their colleagues. And so then their colleagues are running off 100 jobs at a time. And then they start, you know, that's really the ultimate game with these large enterprise companies. They start, instead of having this kind of siloed, you know, there might be an aerodynamics group that's only using it by themselves. At some point, the other groups start figuring out, hey, you guys are doing really interesting, exciting stuff, and this is how you're doing it. They want access to that tool as well. And then it becomes more of an enterprise deployment where every single group gets access to it. And, you know, that's a challenging sales process to go through, but certainly worthwhile, because then once you can start connecting the structures group with the aerospace group, right? And so the structures group starts running problems, and they can start connecting those together and then solve that multidisciplinary problem. And so the levels of value that you get out of that, first it's just about scaling up an individual problem, right? Which is a little bit valuable. So you can run a little bit bigger problem. Then it's about you can run as many problems as you want. So that's a lot more valuable. Then once you connect the disciplines, that's when you start doing true innovation and really running, developing entirely new models that you were never running before. All right, well, thanks everyone for coming. Really appreciate it.